their Excel file. For some reason it's okay. So it's about shooting and hitting the target. The key problem, obviously, when there is a side wind. Okay, so that's what I'm looking at. And then this is view from above. So otherwise, the rest of the data is here. Okay, so the trajectory and the deviation, but this is the how far you deviate from the straight line. As far as I understand, this is a straight line. The target is maybe here. Okay, and then the wind will take you away, and then your choice is to then pick the right angle to shoot against the wind. The data that is variable is at the top, which I already varied a little. Just for fun. So you took into account both the radius and mass using I didn't read the project yet. So what did you use?
I think we had some constants in there for air density, and then we had air drag. Let's see what else.
If you remember the name of the formula that you used, because I
don't think we used a specific formula. We just kind of derived it and just with multiplying or dividing by things to see what we could get.
Okay, I'll read it. And it looks very plausible. Okay, to begin with. So, for example, if I make the wind speed high, then see, then what you shoot is that doesn't really matter. The wind takes it away, and it goes in that direction. So this is the direction of the wind.
Yes.
Okay. So, but on the more reasonable conditions, when the wind is comparable to or less than the speed of your shooting, then this is what you're observing, and you can actually do trial and error in choosing the angle or the muzzle velocity in order to hit the right spot. Okay, so as you can see, there the other two parameters over there are the radius and mass of this cannonball. Okay, so that certainly is what I had envisioned for a project to be done. Whether I'm looking forward to reading it, obviously, because when you can play with it, actually, it certainly becomes much more interesting. I didn't quite get what these are. The rest of these.
The first two, I think, were just from that project done a semester before.
Okay.
And then the fourth tab,
okay.
We tried to play with using the Coriolis force.
Okay.
Because if you
rotation of the Earth, you take for that problem. Or how
yeah, because that would change the trajectory
right,
if you shot it long enough.
Okay. So what's the conclusion?
We couldn't get the data right on it, but you could definitely see that the further it goes with time, the more that it changes from a straight line, just like wind. Like if you would shoot it for, like that would also come into effect.
So I wonder, so do they use it? Did you look up? Do they actually take into account in artillery?
Yeah. Yeah.
So that is fascinating, obviously. So I did a similar thing with the air resistance. Instead of side wind, I did air resistance, and the interesting part of the last semester I did in another class is the Civil War. It's called the range table. So for several values of the angle of the cannon, like 5 or so, they gave you the distance where the cannon's supposed to land. They establish it by trial and error or testing. But then I went back to Euler, which did the work pretty like 100 years earlier, and I was able to produce these results. So those exactly fitting pretty well with the Euler analysis of pretty much similar in nature, just differential equations more than anything. And so that would quite surprise when you can produce something like that. And I was surprised also by the fact that apparently ballistics was not highly developed just yet, even in the middle of the 19th century yet.
Yeah.
So maybe it just wasn't standardized enough in terms of how I mean, you don't go beyond like 5 degrees elevation, so it means that you're pretty much shooting straight. so it worked out pretty well. I was surprised. But then I went to a website which was what's called Home Run Derby, and they post the angle and the velocity of the ball. Okay, and I could not reproduce those results. I guess maybe the ball is different from cannonball.
Oh, you talking? They have a StatCast now where they have the launch angle of the bat and then the exit velocity. Yeah, I know what you're talking.
And that I don't know why for cannonball it worked out fine, and for this one I was not able to reproduce the results.
It's relatively new.
Maybe the spin.
The spin, because each picture has a different spin rate when you rotate through the arm.
Because they do spin it. So if you get it under it, it will spin it, and so maybe it goes farther.
Yeah, there's it'll change. There's always parameters with throwing velocity from the pitcher and the spin rate as well. So that could be something you can look into.
Okay, so I'm looking forward to reading your project and the rest of them as well. Okay, so if other projects you have anything to show, just send me. I'll also try to sort it out and maybe share it as well. Okay, so this is where we are. Just trying to summarize integrals with parametric curves involved. And number one is the very basic. It came from back in September when we found displacement from the velocity. So the answer then would be an input P is a parametric curve and the output is 2. So this is a parametric curve. The output is a parametric curve. In the meantime, the ones that we have considered just recently, the output is a number. The number is the length, or the number is the worst. Either way, okay. So, and the crucial difference is that is really cannot be more crucial than that. Parametric curve versus a number. If you look at the notation for the integrals on the left, these two, you'll see that the difference also is the domain versus the integrand. So either you integrate the parametric curve, then you have another parametric curve, or you integrate either a function or a vector field over along that parametric curve, and then the answer is a number. Okay, so once again, the parametric curve entirely in a different setting. So this one we revisited. Soon get back to it. I will have one more example of also parametric how we can integrate a parametric curve, but this time not along a parametric curve, and this is also along a parametric curve. P is the parametric curve. This was across a parametric curve. So across a parametric curve. And what I mean is we're talking about a flux. Okay, so how much water crosses a curve. So that's roughly the question we want to answer. We don't going to talk. It's just an example, but it really indicates how the variety of problems turn into line integrals. The main difference will be the starting point. Even before you get to the curve, what is the curve and how do you cross it? We're talking about a vector field, but this time the vector field is not a vector field of a force field. So the force works, and the work is the output. This time, instead of force field, we have a velocity field. So all of these have these physics interpretations. So these mathematical concepts have these interpretations. And so if we interpret our vector fields as a force field, then we can have work along a curve on that force field. Or we have velocity field. Then the things change dramatically. And let me try to make that. So one is a vector field. Okay, so say F. Okay, and then we have a curve. like this, okay, C, okay, and then I could have the exact same thing, and totally change the problem. The picture is the same, a problem is different, so the left one is familiar, so this is once again force, okay, F, and then just to make a couple of pictures, so remember we would take the tangent to the curve, and then we project on these tangents, we project the vectors, appropriate vectors. So for example, this one vector, this appears to be 0, this one not quite 0 maybe. So then there will be a projection that gives you the relevant part of my vector field that produces work. Say maybe like this, like this. Okay, so this one actually gives me the negative work in the opposite direction, and well, just happen to be a lot of them are perpendicular. But this one, another, gives me once again a positive work. So these are the projections that in red I indicated. That are projections on the tangent vectors of my curve. Okay, so that adds up to work. Okay, and now we're looking at the identical picture on right, but this F is velocity, and we don't care what's happening along the curve, but rather across the curve. How much? That's what flux is. It's called the flux of a flow. How much of the liquid passes through this curve per unit of time. Okay, so. So if once again I try to do it, then once again some of the vectors will have to be treated appropriately in order for us to understand the problem. And so you see the difference with the crucial difference from on the left and on the right. What vectors do we have to look at? Suppose this is my force, and this is my, not the displacement as much as the tangent line, but well, let's say it is displacement. If everything is constant, then what we are paying attention is this vector. So only the part that is parallel to the tangent matters. The tangent is, by the way, where is my tangent? This is my tangent. I call it D because it's kind of a displacement anyway. Okay, so the tangent, that would matter, just matters. So we're moving along D, and then we're asking how much the force does during that process when everything is constant, and the answer is projection, and the projection is found through the dot product. Okay, so similar but not quite. So my error is not. This is still. I don't want to call it D. Let me still call it T. So to remember this is the tangent line. But from this picture, how do we derive the amount of flow through this straight piece of the graph? So the green one is the direction of the flow. The red one is our, let's say, surface. We zoomed in on that surface and it looks like a straight line. So how much of the liquid will pass through this piece of a line? Compared to the picture on left. Would that be the answer? So work along versus flux across. Okay, you see the difference? What's the difference? Between a along and a cross?
There's now we're going across, then going along.
Well, why would you say that?
Because they're, most of the vectors are going perpendicular to the curve.
Okay, yeah, that's a good point. Okay, so let's, I can totally see what you're saying, but let's make it simpler and look at this picture. So, if you have only one vector and it's not exactly perpendicular, so where is the, what should I look at then? And once again, am I doing this or am I doing something else?
Something else.
Something else, which is what? Across, along? I'm not looking at the parallel part, but rather at perpendicular part. So I draw a straight line which is perpendicular to my line, and then I project my flow. Once again, this is a flow. This is not a force anymore. This flow, I project that flow on that perpendicular line, which will give me then the amount of flow that crosses. You see, when it was about the work, we decomposed our force into two parts. One part along the motion, the relevant part, and then there was a perpendicular part which was irrelevant. It's like, once again, horizontal motion, which doesn't do any part of the motion, that doesn't do anything as far as the gravity is concerned. Gravity is vertical, so a horizontal motion does not involve this force, and then the work is unaffected, that part of the motion. And vice versa. Here we do the opposite part. We also decompose, but we pick the other part of the vector of the component. So there are still once again two vectors, but we pick, it's the exact same picture. We pick here this one, and here we pick that one. Why? Because why is this irrelevant part? Well, imagine that there is no red part. What's the flow? Like this. How much does this flow, how much of this flow cross this straight line? What's the answer?
None.
Flux is 0, right? Because it simply slides along a straight line, so there's no crossing. Just like every motion in this direction will produce no work for the force. Okay, so that's the switch that we made. And that affects naturally the our integral. It is still a line integral, but the difference is quite crucial because we have to first find the vector. That vector over here is called n. That stands for normal. So instead of having just our d being the tangent line, tangent vector of our curve, and we used it directly right there on P prime over there, right? So we have to take it. It's still over here. This is still my t, which is P prime. Okay, so P prime. Okay, but now I have to find the normal vector to it, and well, it is not entirely new, but if P prime is equal to, say, P cubed, what's n? How do we rotate it 90 degrees, if you remember? Well, there are two ways. There are two normal vectors, so it is crucial to pick the right one. But the general idea, you just have to remember we did it once when we did the rotation of relational vector field, and you flip the two x and y and change one of the signs. So it could be, for example, a negative q and p. That's a normal vector. Not the whole story here because what it gives us too much information, because it gives us also depends on how fast we're moving along that straight line. Okay, so which is totally irrelevant because the parameter curve only used to parameterize the curve, and how fast we're moving, we are parameterizing the curve, and there is no motion otherwise. And so we're moving fast along that curve, slow along that curve. The answer should be still the same. So the answer is we make it a unit vector. So we divide it by p squared plus q squared. The unit normal vector. So then the flux is, to begin with, rather the crucial part of the flow will be just as we had over here, the dot product. We once again, here we projected F on D, and here we are projecting on N. But it's still the same thing, we just have to do the normal vector. I'm sorry, we are still doing the dot product. So the dot product here, and we're still doing the dot product, except it's going to be now, what is it, F dot N. Okay, so we're projecting F on the unit normal vector at that location. Okay, so so that's not the flux, but I don't think there is a, well, let's say just the amount of flow through that point. The flow across C is F dot product N. Okay, so that the red part. So N is. Oh, let me change this. This is really not N. N is the little one. This is N. The unit vector in the perpendicular direction. But rather what I have here is F dot N over here. Okay, projection of our velocity field on the unit normal vector. Okay, so that gives me the function to do what with it? To integrate. Okay, to integrate across the whole length of the curve. So we establish whatever is happening at every single point. It is described by this function. F dot product N, and now we just integrate along the whole curve, and this is the final product in this formula. So the flux, the total flux, total amount of the liquid crossing the curve will be the integral. So the notation is slightly different. So it's C F dot N. I'm sorry, just dN dot dN. Okay, so it was D or dP, where P stands for that parameter curve, and now we have dN, where N stands for the unit normal vector to P, our parameter curve. Okay, so that's the notation, and then we already know how to write it out. It will be integral from A to B. Once again, our parameterization is x is equal to P of t between A and B. Okay, and now what are we integrating? F first, and once again, look at the, everything will be repeated what we have in this formula, except that last part will be where we have P prime, we'll have instead N. Okay, so it will be F of where the location, which is P of T, okay, same composition, dot product with N of T. Okay, so that normal vector to the parametric curve, and dt, that's all. Okay? So the flow, the starting point, but really what we care about is the flux. We can compute it with Riemann sums, or since we already know how to do it, we did it once. The computation is almost identical. There is one extra step, and that is the, in comparison to the last one, it is the computation of the unit normal vector. Okay, so just an example, just one example of the computation. So let me take a circle. Well, let's take this problem. Okay, so this is my C, and let's make F a very simple vector field. It's just totally vertical. So this is my the flow is through half circle. They parameterize in the usual way, radius 1, and force is simply 1, 0, 1. Okay, C is upper half of the unit circle. So as you can see, it's quite transparent what's going on. But the computation certainly will require some integration and differentiation. Because the direction of the vector varies. Direction varies, but you can already tell what is the answer: positive, negative, or 0. The flux. It's positive. It's every single one of them, except for at the endpoints, will be strictly positive. At the endpoints, the flux, the flow will be 0. There will be no crossing of anything at the two endpoints because they are actually tangential. Okay, so the flow coincides with the tangent line over here and over there. But otherwise, everything is positive. Okay, so now so find flux is the problem. Okay, so we proceed to step number 1 to parameterize the curve the usual way. So P of t is cosine t sine t, t between 0 and pi, half of the circle. Okay, then we're going to need P prime, which is once again negative sine t cosine t, with the same interval. Okay, now computing the normal vector. So n of t then, flip with change sign. I guess I put the negative sign in the wrong place. Okay, so cosine t sine t. Okay, so if you are not sure what you have found, I showed you the quick way to do it, but you can always verify whether or not two vectors are perpendicular by doing what? Dot product. So dot product, multiply these and you get 0. So these are normal. Okay. In fact, to verify well, you got to verify that your answer makes sense if it's possible that you have chosen the wrong of the two normal vectors. Here, as you can see, I chose the correct one. These are the ends, by the way. The only I'm sorry. This is it is the end. Why? It was slightly easier than normal because the vector is already a unit vector. Otherwise, you have to make that extra step. Okay, so these are my normal vectors. And then I plug in then for the flux. I plug in them into the formula, integral from 0 to 2 pi. F, no worry, this is simply 0, 1 multiplied by the normal vector, which is cosine t sine t dt. Okay, so we're getting from 0 to 2, I'm sorry, not 2 pi, just pi. Sine t dt. Okay, and there you go. So we have cosine, negative cosine t from 0 to pi. Yeah, so I didn't choose the right one. Sorry about that. How did that happen? Sine t. No, I'm fine. Okay, so it will be, what is it? Cosine of pi is negative 1, and negative 1 minus negative 1. Well, minus 1. So it's negative, hold on a second. No, it's positive 1 plus 1. Okay, so it's 2. So cosine of pi is -1. Cosine of pi is -1, so negative is 1, and cosine of 0 is 1, so we have 1 plus 1 is equal to 2. So positive flow, okay, so any questions about how we did this? So parameterization, derivative, normalizing it, no, not normalizing it, but rather rotating it 90 degrees, making sure that it's the right unit vector. You will know whichever, if you end up with a negative flow while it's supposed to be positive, then you'll know that you messed up, you picked the wrong one. Okay, then normalization whenever necessary. We did not have to do it. Plug in into differentiation. Every time with all of these integrals, after that product we end up with nothing but a usual calculus 1 integral, and then you have the answer. So the answer is 2, and I wonder, can you see, could we have guessed the answer? Unit. Okay, and these are my this is my flow. Okay, do you see a 2 without any computation? There's a 2 here somewhere.
Can you just multiply by the normal vector at the top?
Normal vector at this, over here?
Yeah, the top.
No, I don't. No, it's it is still 1. This is still 1. Every single vector is a 1. Okay, a vertical. The length is 1. Pointed vertically. The integration, even though it was easy, but it was a legitimate integration. The function sine is variable, so what you can see here, a variability along the curve. Is in fact we have to take care of in the hidden projection that we described before. We didn't have to worry about anymore. Is right there, the dot product over there. That's the projection. So where's 2? So this is 1, and all of these are 1s. Where's 2? You see any 2 here?
Diameter of the
What?
circle.
The diameter of the circle is 2. This, in fact, specifically, this is 2. Okay, so how does that help? Any guesses? Well, okay, ask yourself. Ask yourselves, what is the flow across the diameter? Flux. Flux across the diameter. So one particle, for a period of time, there's say one particle crosses it, and the length is 2, so you just multiply 2 by 1. Right? So, I mean, you throw out the rest of them. The curve doesn't matter anymore because this is a picture. This picture cannot be any simpler. Well, except these have length 1. And so the length of the crossing, the front of the, well, imagine this is how I would explain it like this. So these particles will start here, and after 1 second they end up over there. The whole front shifts like this, and then the area of this out of the proportion graph, rectangle will be 2. 2 by 1. Okay, so 2 by 1, so this is 1, So the height is 1, the width is 2, and the total flux is 2. Okay? So it's 2. Okay, so this is 2. The flux across the diameter is 2. So can you argue why? What does it have to do with the original problem? Well, think water flowing in a very simple manner. So then, well, the logic is roughly is that as much it is the region which at every point of time contains the same amount of weight. It means that the same amount as comes in has to come out. So it comes in, 2 units come in, then 2 units have to come out. Okay? Or orient like this. Okay, so that's the idea of the flux. And well, in fact, there's more to it, slightly more to it. Another way to explain it is to look at the region as I described it, coming in and coming out. What if I take the region and just close it, sort of, like this? Okay, so the whole curve, the curve will be half circle, not only half the circle, but also the diameter. In the amount of water, if we look at at our field, there is no new water appearing. It is flowing, so there is no source or sink in the region, right? So which means that property that I tried to explain is that the amount of water holds. It will be the same amount of water will remain constant within the region. Okay, so which means that, as I said, the amount of water that comes in here through the well, not in this manner, but that doesn't really matter what in what manner it does, as long as there are no sinks or sources inside of the region, the amount of water coming in and coming out will be the same. Okay, so and that's the argument why it's supposed to be 2. So in other words, you can, under certain circumstances, when once again there are no sources or sinks, you could try to avoid a complex curve. You are asked about a complex curve. That's not your choice. But then you can instead pick a simpler one, like a straight line. And your computation will be very trivial. So what I did over there, it is also an integral. It's the same definition applies, except the function is constant and the curve is constant. Therefore, the whole computation turns into simply multiplication 2 by 1. 2 by 1 is equal to 2. That's how we found the flux across the diameter. So it is the same idea applies to work, by the way. And it is kind of related. That we're gonna, well, let me put it this way over here. There is a notation for the line integral. So let me call K a closed curve. Make it a full circle. We use the extra circle to emphasize the closed nature of the curve, and also putting an arrow there. We use that extra notation. So not just a line integral, but an integral along closed curve. Okay. So and then what we're saying here is that under these circumstances there is no source. The answer is such a or sink. Then the flow is 0. The flux is 0. Nothing coming in, nothing coming out. Okay, so and then what is the analog of this statement, which is actually more important in a sense? When we talk about the work, it's pretty much the same thing, and the integral is also the same. So we would have integral with a circle, with the arrow, over k, but we would have f dot dp, where p is our permitted current. So this one is simpler. So once again, this is flux, and this is the same setup, the same vector field, same curve, but this time it is about the work. So we're circling back to work, and it is, as you can see, slightly simpler. So because you don't have to do no normalization, And what is the meaning of the work on a closed curve which is closed? It means that we are not, that it is that we would call it a conservative vector field. So conservative. Conservative, such as a constant vector field is conservative, the gravitational vector field is conservative, so circular motion gives you zero, the work cancels out. Okay, so if you go up a hill and against the gravity, then down the hill with the gravity, they cancel out. Okay, so that's roughly what happens. So whenever F is a gradient vector field, it is also conservative, and we have a work along a circular curve. It cancels out, and net effect is zero. So these are two very parallel computations, parallel ideas. We will concentrate on the previous one where we started. And this one, I like this one better in a way because it's, well, one reason is because you don't have to refer to forces because the idea of flow is much more broad than the physics of forces and work, which is how we explain this. Anything can flow. Anything can flow, and so it could be not only liquid, any kind of material can flow, heat can flow, people can flow, anything, money can flow. All of this is equally applicable to velocity fields. So once again, velocity field here, work fields are there. Another thing, however, the drawback of this is in Rn. This is in Rn, and this is in R2. So we measure work along a curve in any space of any dimension. It's not working out as easily for fluxes because well, you can tell me. So if this question was definitely two-dimensional, so we had a curve on the plane, and we measured the amount of flow across that curve. What would be the analog situation in dimension 3? So the question is, once again, how much flux across what? How much water has crossed, or let's pick air, so that it would be no confusion. Air is definitely three-dimensional. So how much air, there's a wind, okay, it's how much air crosses what? Curve or surface? A plane or a surface, yes. So as you can see, we immediately will lose the connection to curves because flux in three-dimensional case will be flowing across a surface or a particular plane. And which means that we're really simply not prepared to talk about it because we have not talked about parametric surfaces, only parametric curves. And then this would have to study fluxes. In high dimension, we have to have, in dimension 3, we need parametric surfaces. In dimension 4, we need parametric spaces of some kind. And so it becomes just more complicated. Parametric curves is a fairly manageable topic, and we started early a while ago in Calculus 2. But parametric surfaces, well, we haven't had any time for that. So we proceed with this. And we are back to the problem of conservative vector fields versus gradient vector fields, and rotational, irrotational vector fields, and that is what we're going to be deciding. Meaning that is the exact problem here is demonstrated. I have 1 minute left, so let me show you how this works out. What if f is a gradient vector field? So it's del of some function f. Then let's see what that integral is equal to. The integral will be equal to, from a to b, f capital for the vector field. Here I have, I'm sorry, I meant p. No, f. Okay, what is f is the gradient, and I'm integrating f of p of t. Well, it's not f anymore, but this is del del f dot p prime of t dt. At this point, you're supposed to recognize this formula. What is this? Should be familiar from not long time ago. Del is derivative, one derivative, p prime the other derivative, multiply them together when we do this.
Does it work?
What?
Does it work?
What part?
Work.
No, I was referring to something more mathematical. The product of two derivatives, when do we have it? The product of two derivatives? Or something is the product of two derivatives. What is it?
Talking about channel.
Yes, the channel. Okay, so that's the channel. Okay, so we do it next week. And then it simplifies and you get 0.